So hello everyone, welcome to the third video of this lecture series Semiconductor Physics. So in our earlier videos we have already discussed about what is semiconductor, classification of semiconductor, the extrinsic and intrinsic semiconductor, and particularly extrinsic semiconductor, what is extrinsic semiconductor, and how we can improve the conductivity of a semiconductor by adding some kind of impurities. Those are called, this is called doping method. And there we found two types of extrinsic semiconductor. One is p type and another one is n type. And lastly we have already discussed about the energy band diagrams of the p type and n type, how the energy levels are distributed, how the electrons are being transferred from the valence band to the conduction band. So in this video we'll discuss about these following topics. One is like PN junction diode, and then diffusion and drift current, and biasing conditions like forward and reverse bias, and the IV characteristics of them. IV means current and voltage graph. Basically we will discuss about them, how it behaves in these type of circuits. So let's get started. So first one is what is a PN junction diode. So what do you mean by a PN junction diode? PN junction diode is nothing but a crystal which is made up of two type of extrinsic semiconducting material. One is P type and the other one is N type, right? Okay, so it is which if we talk about it is basically a unidirectional element. Okay, so what is the unidirectional element? Suppose you have seen the example of a resistor. Suppose this is a resistor, right? Okay, if we put a voltage source here, okay, voltage source, DC voltage source basically, then what will be the current? I equal to V by R, and and the resistance of this resistor obviously R, and the voltage is V. So current is flowing here, we can say, from left to right. Suppose we change the direction of the, suppose we reverse the polarity of the voltage source, right? What will happen? The current will basically move in opposite direction, means right to left. So current here can flow from both directions, whether depending on the polarity of the voltage source. So it can move from left to right, also from right to left. Okay, so this will be a bidirectional element. Okay, so there is no there is no change in the current value, but the direction is changing. So it is a bidirectional element. Okay, so but PN junction diode is not a bidirectional element. So PN junction diode is a unidirectional, means only in one direction the current can flow. Okay, as register, you can take the example of a capacitor. Capacitor can also allow the current from both directions unless and until it is charged. Okay, and inductor also. So these are kind of bidirectional elements, but uh, PN junction diode is a unidirectional element. Okay, so there are two processes involved in this diode basically. Okay, two different processes occurs during this diode, and these two are basically diffusion and drift current, and it happens generally during unbalanced conditions. Okay, unbalanced means the unbiased condition. What is unbiasedness? Basically absence of voltage source, absence of external power supply, we can say, also external voltage source or power source or current source. Okay, so external voltage source we can simply write. Okay, so we have a detailed discussion of these two processes. Okay, so first one, what is the diffusion? Okay, so there is p type and n type material in a diode. Okay, as we have learned. So what is p type? Here basically p type is p type impurities are added. So here majority charge carrier are holes. Okay, so sorry, so here holes are majority charge carriers, means plus charge basically. Okay, and here electrons are majority charge carriers. So what happens basically, if here we have not connected any external thing, okay, it is just simply as a diode, unconnected with, not connected with any other else element, any other circuital elements, okay. So what happens basically, you know, right, the concentration, okay. So here the concern in p type, you can say the hole's concentration is more than electron, and in n type the reverse is happening. Basically the number of electron, or the concentration of electron is more than the holes, okay. So what happens basically, holes will try to move from p type to n type holes, and electrons will move from n type to p type. So why? Due to concentration gradient, because there is a flow from high concentration to low concentration. That's why there will be some current flow, okay. So the p side of the junction is rich in holes, so, and the n side is in electrons. So due to concentration gradient from high concentration to low concentration, the holes will move. So what happens basically, it will have some energy. So like as they are moving, so it is moving due to some kind of energy, but they will be stopped at some point, okay, and they will try to accumulate in a region. Here you can say that is called depletion layer, or depletion region, you can say depletion region, okay. So the plus charge, no, plus charge, or you can say more appropriately, the holes will basically deposited near the n side semiconducting material, and towards p side the electrons will be deposited, okay, near that layer, okay. So here will be a charge accumulated layer which is called as depletion region, okay. So this depletion region, what happens basically, there will be some potential developed, obviously, because the charges are distributed in this depletion region as plus and minus. So why it is being stopped here? Because it is being stable here, so it has some energy initially and it tries to move towards n side, but at some point it get stabilized, okay. At that point it gets stabilized, so it is present near somewhere like that, okay. So there is some, and similar thing happens to electrons, so there will be a depletion region created, okay. And that depletion region basically creates a electric field, we can say. So electric field sets up a potential difference, of course, okay. So this potential difference is called barrier potential. Here we have written, okay. So here you can see that barrier potential is generated, okay. So near this region, you can say this is the our barrier potential, okay. So this is our barrier potential, and here we have p and n type semiconducting material, okay. So here you can see also, um, just a minute. So here you can see this is p type and this is n type, so they are distributed like this, and this region is called as the barrier, sorry, depletion region, okay. And it creates a electric field, depletion region, and it creates a electric field from n type to p type, okay, from n type to opposite, n type to p type, okay, just opposite to diffusion. So it creates a electric field, so there will be some potential difference. That potential difference we call as barrier potential, okay. So next, so this barrier potential basically opposes the diffusion of holes and electrons across the junction. So what happens basically, sorry, so here you can say like this is our PN junction diode, okay. So it is p type and this is n type. So holes are moving towards this side due to diffusion. So holes are moving from the p side to n side, and electrons are moving from n side to p side. So there will be a diffusion current from p side to n side, because current direction is just opposite to the electron movements, okay. So there will be some diffusion current from p side to n side, okay. And what happens right now, we have created, there is some depletion layer is created due to accumulation of charges, okay. So that will set up a barrier potential, right? so that is called VV. So that also what it does is basically there are some after accumulation of the charges, what it does is in n-type semiconducting material, you know, right, there are holes are the minority charge carriers. Okay, holes are minority, sorry, minority minor sorry minority charge carriers. Okay, and here electrons are the minority charge carriers. Okay, so what it does is basically the this hole will be forced by this electric field from n side to p side, and the holes will move from n side to p side. So there will be a movement of current, sorry, so there will be a movement of current from n side to p side, which is opposite to the diffusion current. So it is our diffusion current. In opposite side, we have a current that is called drift current. Okay, we'll discuss about that. So this is our net current equation. Okay, so diffusion current minus drift current. Okay, so what we have discussed basically, there is due to concentration gradient, the holes will move from p side to n side and electrons will move from n side to p side. So there will be a current due to diffusion from p side to n side, and that is I diffusion. And due to setup of the barrier potential, the minority charge carriers from n side, the holes basically will try to move from n side to p side, and that current sets up the drift current. So our net current equation can be diffusion current minus drift current. Okay, so that we have basically discussed. So what happens basically now, this is basically diffusion current we have already discussed from p side to n side due to concentration gradient. So what happens after that, diffusion current will not set up because the charges can't travel because there is some barrier potential, right? Okay, so it opposes this flow of electrons, so EBB amount of energy is required. So this suppose we tell it as VV amount of potential, barrier potential is there. So here if one charge wants to travel, okay, Q charge wants to travel from p side to n sides, it needs energy of QBB in order to compensate this barrier potential, and it can cross from p side to n side. So that energy can't be get because of after some time it will not get that much amount of energy sufficiently to get into that. Okay, so what happens basically, due to that our drift current is also there. So what is drift current? And all these process, this diffusion current and drift current are occurring simultaneously. Okay, so and there is not like that first diffusion current, like diffusion current initially start, right, and then simultaneously drift current will also start after some, like after some very microseconds delay, the drift current will also start. Okay, and it will oppose each other basically. Okay, so what happens during equilibrium conditions? So what we does is, here is a, so this is basically PN junction diode symbol. Okay, so if we connect it to a external power supply, okay, V, and it is suppose 0, we initially set it as 0, there is no voltage source. So if we measure here the current will be 0 basically. So what is happening, our net current is basically 0, and what I told just, net current is our diffusion current minus drift current, minus drift current. So this difference should be 0. That means our diffusion current and drift current must be equal, right, during the unbalanced condition, okay, or the equilibrium condition. So here we have written that the drift and diffusion current are equal to each other and opposite to each other, and they are equal basically. So there will be no current flow when we have not applied any kind of voltage source. Okay, so next is our barrier potential. Barrier potential depends on various factors, like what will be the width of the basically barrier potential. So there are basically three main factors. One is temperature, and another one is the nature of the semiconductor, and other one is the amount of doping. So first we will discuss about temperature, how temperature affects the barrier potential. Suppose we increase the temperature, okay, So what happens towards our junction? So Pn is there. So holes will get so every charges will get external kinetic energy. So they will try to move from P to N. Okay. So basically here what was happening initially, here you have plus charges, right? Okay, so due to external kinetic energy supplied by the temperature, they will not be stabilized here and they will try to move here. So this depletion layer length will decrease basically. Okay, as it was before, there will be, or we can say like at certain point, like we can say the depletion layer region is very small here due to increase in the temperature, because temperature, as the temperature will increase, the mobility of charge carriers will increase. Mobility of charge carriers will be increased. Mobility of charge carriers will increase, right? Okay, so this is like we can say, then the depletion layer width will decrease. So temperature is inversely proportional to width of depletion layer. Okay, dl means depletion layer. Okay, so next is our nature of the semiconductor. Okay, suppose we take the example of a silicon or germanium. The typical value for barrier potential, you can say here is 0.7 volt and here is something around 0.3 volt. Okay, why it is happening? Because you have seen, right, nucleus is there. Okay, and surrounding it outermost valence electrons are there. For both silicon, if you see the periodic tables, silicon is there, and below to that germanium is there. Okay, so why even in the same group, why they have difference in the barrier potential or the width of the depletion layer? Why? Because they are from, if you go down, the number of the like number of protons will increase, but and for both of them the outer valence electrons are 4 only. For silicon also we have 4 valence electron, and for germanium also we have 4 valence, sorry, we have 4 valence electrons. Okay, so what is happening basically, electrons are basically same number of electrons for both of them. So but the distance from the nucleus to the electrons, although it has more protons, for germanium the number of protons are more, but still due to increase in the radius, okay, from silicon to germanium will go, then the radius will increase, there will be decrease in the attraction force from the nucleus. So for germanium the electrons are loosely bounded. Okay, so electrons are loosely bounded for germanium. So what happens basically, due to which the depletion layer width will decrease. Why? Because electrons are more mobile here than in the silicons. Okay, in silicon they have some attraction force due to this nucleus, but in germanium that attraction force is less than the silicon. That's why this depletion layer width is basically decreasing, or the barrier potential is basically decreasing. Okay, so it is basically okay, so and that's the thing basically, it depends on the nature of the semiconductor. So next one is the amount of doping. So amount of doping, we can simply say, suppose this is a diode, okay, initially we have supplied p1 and n1 concentration. Okay, then we have developed another diode which has p2 and n2 concentration, and here basically p2 concentration, p2 is the concentration of the holes here basically in this p-type material, and p2 is greater than p1 and n2 is greater than n1. Then obviously there will be more charge carriers, more mobile charge carriers. That's why what happens basically, this they will be not stabilized here. Okay, here holes and electrons are not stabilized, so the depletion layer width more depletion layer width basically decreasing in more. So depletion layer width decreases. Okay, more. Why? Because they are more mobile charge carriers. Here also we have told, like if we increase the temperature, the mobile, we have more like we have more charge carriers are more mobile. So here basically what is happening, due to more majority charge carriers, they can easily flow from here to there. So amount of doping, if we increase the doping, basically the depletion layer width will decrease. Okay, so width of DL or width of depletion layer will decrease basically. Okay, so barrier potential for silicon is 0.7 volt and for germanium is 0.3 volt. This we can remember, and this is the typical symbol of a PN junction diode. Okay, so this P type we call as anode. Okay, this is convention basically, and this is cathode. Okay, so next one is like width of the depletion layer. Here I have already discussed, like if the doping concentrations are small, then the number of electrons and holes are basically less, so the depletion layer width will be large basically. But what happens if the reverse is happening, basically high amount of doping concentration is there, then the holes and conducting electrons are high and the depletion layer width will be small because they are more in concentration, so they will easily flow from p side to n side and from n side to p side. Okay, now what happens now, these all are we have already discussed for the unbiased condition. That means we have not applied any kind of external voltage source. But what happens if we apply external voltage source? So that is called basically bias condition. And in this bias condition also, earlier we have already discussed about that PN junction diode is a unidirectional element. So the voltage source can be connected to the if it is the PN junction diode in this direction or in the opposite direction like this. Okay, so it can be connected like this, right? Sorry, so like this it can be connected, right? So what happens for both these cases? So we have two cases basically, two biasing condition. One is forward bias and another one is reverse bias. We'll discuss about that. Okay, so first is the forward bias condition. So what happens in the forward bias condition? Basically the positive supply of the voltage source is connected to the P type. So here if we draw like this symbol, so this triangle side is P type and this line, vertical line, is basically N side. Okay, if this positive terminal of the battery is connected to the P type, then it is, and negative is connected to the N type, then it will be called as forward bias condition, right? So the applied voltage is now there will be voltage. Okay, now we'll go to the PN junction diode. Okay, so here we have PN junction diode and there is some depletion layer, right? And here are our holes and here our electrons are there. So if we connect a external voltage source, right? So what happens basically, the electrons now our applied voltage in this direction, and there is some opposing voltage, right, due to barrier potential. So we have our net equation as B minus BV. Now this external voltage source should be greater than VV so that we can pass current through this PN junction diode. So what is our requirement for the voltage source or power source is should be B should be our external voltage source should be greater than the barrier potential in order to pass the current. Okay, so the current will flow from P to N here, obviously because we have positive source is connected to the P side and negative source is connected to the N side. Okay, so if we increase this voltage, the effective resistance will decrease. Why this is happening? Basically because if we apply the voltage more, we'll put a demo also here. So if electrons are more deposited, like from the negative end of the battery, electrons will come this side to the end. So here electron concentration will be more, and here protons concentration or holes basically you can say, so positive charge concentration will be more. So if they have more majority charge carriers, then they will try to move from P side to N side. due to which this resistance, why, what is resistance? Basically that is opposing any current. What is the definition of resistance? Any circuital element which is opposing the current flow is called a resistance. So this effective resistance is getting decreased if we increase this voltage. If V is increasing and VV we have some fixed potential, then the current will basically increasing. So basically this resistance, the of the flow of like the opposing force behind this is basically decreasing. Okay, so the effective resistance will decrease. We'll so see also the graph IV characteristic in there we can get. So this is basically the in there we can get. So we can see here the model of the forward bias condition for the PN junction diode. So this is our external voltage source, and this is the PN junction diode. This is P type, and this one is the N type. Okay, so due to development of the depletion region, there will be barrier potential VV, and there is the external voltage source V supplied by our battery. Okay, so initially what happens, the electrons from the negative end of the battery will go towards the N side, and the holes from the uh, or plus charges, basically we can say, from the positive terminal of the battery will go towards the p-type semiconducting materials. Okay, so it is like that, and this is like that, and this will eventually pass from this barrier potential. Electron will move from n-type to p-type, and also will move from p-type to n-type. So there will be a current from p side to n side. So this happens during the forward bias condition. And as we have to as I have already told you about, like, there is barrier potential VV. So due to this barrier potential, this V should be greater than VV. So initially when we apply from 0 voltage to VV, so external voltage source, if it is equal to VV, so 0 to VV, then sorry, the external if V is coming from 0 to the potential VV, then what happens, basically the initially the current will be very small. Okay, at some point VV, the current basically starts to flowing very large. Okay, so if I draw you the ideal characteristics of a diode, suppose this is like that. Okay, so this is our potential and this is our current. Okay, so initially from 0, if we apply 0 potential, sorry, if, if we apply 0 potential, then no current will flow, and here it is, suppose VV current, VV voltage source, like barrier potential is there, and then from 0 to VV the current will be very small, means 0 we can say basically, and at BV the current will try to shoot up. Okay, so the current will be very large. Okay, after VV. Okay, so this is basically the ideal forward bias characteristics of a diode. So this barrier potential, which we call basically the cut-in or threshold voltage. Okay, so after this, basically what is happening here, basically after crossing this VV, it is becoming short circuited. Okay, if we take the example of a basically ideal diode, okay, which is not available in the market. Okay, so it will be basically the circuit will become short circuited. So initially if the circuit is looking like this, okay, so initially the circuit is looking like this, but after V is greater than VV, the circuit will look like something like this. Okay, so there is resistance is nearly zero. Okay, so the voltage, the current will be basically infinite, means if we increase slightly more than the VV, the current will try to shoot up. Okay, so what happens here, so then the current increases exponentially on increasing the voltage, but this happens why, due to real characteristics of diode. So there is no ideal diode exists that the current will be very infinite or will be so much large. Okay, so it will increase basically exponentially. So the forward resistance is becoming very small. Okay, so you can see here the ideal characteristics of a diode initially at 0 voltage. Okay, so initially at so sorry, so initially at 0 voltage, the current is also 0 and voltage is also 0, so V equal to 0 and I equal to 0. Then it will try to increase very small, very small, very small, and there is a point where cut-in voltage is there or threshold voltage is there, which we call as barrier potential. So after this, the current will try to shoot up in exponential manner. Like, I am not drawn properly, but this is like actual characteristics of a diode. So which is available in our market. So it is basically the silicon diode. For that's why the forward bias voltage is basically 0.7 volt. For germanium it will be 0.3 volt. Okay. So, and the current will get in terms of basically milliampere. Okay. Now is the second case, the reverse bias. We have already discussed about the forward bias. Now we'll discuss about the reverse bias. So what happens in case of a reverse bias diode? So this is our diode, right? For forward bias, we have connected, this is our P type and this is our N type. Okay, so for forward bias, we have connected the positive supply of the battery towards the P type. But in case of reverse bias, this happens basically opposite. Means our positive end of the battery is connected to the N type and negative end of the battery is connected to the P type. So what happens here basically? So when a positive terminal of the battery is connected with the N side and negative terminal of the battery is connected to P side, that is called as reverse bias current condition. That means we are supporting the barrier potential, right? Okay, so there is basically barrier potential is getting supported. So basically we are applying voltage V plus VV. So one can say basically the current will then move from N to P side. That doesn't happen basically. Doesn't happen. Why? We will discuss about that if we go to detailed structure of the PN junction diode. Okay, so no current will flow basically till it reaches the breakdown voltage. There is like there is some cut-in voltage. Here one breakdown voltage is there, and this breakdown voltage is of two types. We will discuss more about that in upcoming videos. One is avalanche breakdown, and another one is Jenner breakdown. Okay, so these two will discuss more on upcoming videos. Okay, so till now you learn know basically, there is no current flow till breakdown voltage. After the breakdown voltage, again the current will flow shoot up basically. Okay, so what happens on increasing voltage, the effective resistance is increasing. Why? So if we because majority charge carriers move away from the depletion layer and hence increases the width. Okay, so if we just draw the PN junction diode diagram. Okay, so this is our PN junction diode and there is depletion layer, right, in unbalanced condition. Okay, we change the color. So here minus plus charge are there. Okay, and here holes are majority charge carriers, and this is P type and this is N type. Okay, so here electrons are majority charge carriers, and we have connected the battery like this in opposite manner. Okay, so what happens here is basically holes will plus charges will move from this side to this side. Okay, so this depletion layer width will increase. Okay, that means this opposing potential or opposing barrier potential or VV is basically increasing, right? Okay, so that's why our effective resistance, okay, effective resistance is opposing the flow of electron. Effective resistance is increasing, so it is opposing the flow of electron because our depletion layer width is increasing, right? So there is no majority charge carrier flow. That's why there is no current flow basically. But after a certain point, which we call as breakdown voltage, the current will again shoot up. Why? Because there is basically these bonds will try to break here. Okay, so whatever bonds are there, this plus charge and minus charge have some kind of covalent, like not covalent but some kind of bond pairing is there, but that pairing basically break down after a certain threshold limit, that is breakdown voltage. So if we saw, so the majority charge carriers here we have already discussed, like the majority charge carriers move away from the depletion region layer and hence increases. So the majority charge carrier will try to move away from the depletion layer. So this basically if it is plus minus like that, so it will move away, and this depletion layer width will be basically more and more and more if we increase this reverse bias voltage. Okay, so the depletion layer width is increasing basically. Okay, so here you can see the plus charges is getting accumulated here. Okay, and the negative charges will go from and this is obviously p type and this is n type. Okay, and this plus charge will not settle here, it will go towards this side, and because after pulling there is no one plus charge is there, so it will get struck here. Okay, so there will be more number of positive charges will go and go, so this can't be stabilized, and this layer basically our n type is becoming more p type and p type is becoming more n type, so this depletion layer width will increase. Okay, that's why it opposes the flow of majority charge carriers, due to which there is no flow of current basically. So reverse bias characteristics is basically initially the current remains constant, that is very small. Okay, and that current is basically due to minute minority charge carriers, and that current will be very small, and we can say it is in microamperes basically, and this current is called reverse saturation current. Okay, because the current is flowing in opposite direction, right? So then the reverse current increases exponentially after increasing the voltage in opposite direction. The point after which the current increases sharply is called breakdown voltage. So this is called breakdown voltage. So after a point the current will shoot up. Okay, that voltage is basically breakdown voltage, and this is of two types. One is our Jenner breakdown and another one is avalanche breakdown, which we will discuss in the upcoming videos. Okay, so the reverse bias resistance is very small, but after some time, like after we apply some kind of voltages like in the reverse direction, this resistance will try to increase. So initially it is very small, here I have done something wrong, but it is very high actually. It will be very high. Initially it will be small, but after applying some resistance, this reverse bias resistance will increase basically. Okay, so here you can see the typical graph of the reverse bias characteristics. Okay, so initially at 0 voltage current is 0. Okay, then after that some due to minority charge carrier there will be some current flow, but it is very small in microamperes basically. Okay, and and it will tend to move and move and move, and after a point there is Zener breakdown, or we can say breakdown voltage, or we can say avalanche breakdown. So after that the current will again try to shoot up. Okay, and this current will move in opposite direction, and it will be in like infinite, we can say. Okay, so breakdown, why it is happening? Because of the breakage of the bond between the hole and electron pair. So in the depletion region basically what we are doing, like what is happening basically, holes and electrons are getting paired. This pairing or this bonding will get break after this breakdown voltage. Okay, and the current will move from n side to p side, and this will shoot up at the breakdown voltage. Okay, so that is it for today guys. We'll meet in the next video. Thanks for watching, and please subscribe to my channel if you find it helpful. Or